projection on a Banach space. So, projection on a Banach space. So, what is projection on a Banach space? So, very important concept, very important. Now, first go through the definition. What is definition of a projection? So, projection on a Banach space, a projection on a Banach space B is a idempotent operator. Idempotent operator. So, definition of a projection is: projection on a Banach space is an idempotent operator on a B, on a Banach space B. So what it means? It means E is, suppose E is a projection on B. What is B? B is Banach space if it satisfies two conditions. Condition number 1, E is idempotent. Idempotent means E square is equal to E. Condition number 2, so E is continuous. Continuous means bounded operator. Continuous. Or we can say that bounded operator. Bounded operator. Bounded operator. So, in the operator, bounded condition is involved. So, it means the definition of a idempotent projection is a idempotent operator. So, idempotent operator means it is a E square equal to E and E is a continuous. We can say that E is a bounded operator. So, just understand this concept. A projection P on B, a projection P on a Banach space, on a Banach space B is described as, can be described as, so it can be described as: number 1, a projection determine a pair of linear subspace. Number 1, a projection determine pair of subspace. So this subspace is called M and N such that B is equal to M, its a direct sum with N. So B is the direct sum of M and N. So what is M? So where M is null space of P, M is a range of P, and N is null space. Range means P of X such that X belongs to B. So what is this? It is a range of P. So what is this? It is a range of P. So what is N? So it is a null space. Null space means X belongs to B such that Px equal to 0. So this is a null space of P. So this is a null space of P. So it means a pair of linear subspace such that B is direct sum of M and N determine a projection whose range and null space are M and N. So remember this. Also, in addition to that, if I take X vector belongs to B, so what is B? B is a direct sum of M and N. So direct sum means every vector in B can uniquely express as the sum of these vectors. So if I take it is a Z vector, so Z vector can be written as X plus Y, where X belongs to M, Y belongs to N, and this expression is unique. This expression is unique. If this expression is unique, so P of Z, which is equal to P of X plus Y, since P is a linear operator, so P of X plus P of Y. Y belongs to null space, so this is a P of X, and P of X which is equal to X. So P of X which is equal to X because it is idempotent. So P of X is equal to X. So it means P of Z can be written as P of Z can be written as X. So remember this result also. Clear? So this is a P of X because X belongs to range. So X belongs to range. So this is of this type. So P of X is equal to X. So in the range its value is equal to itself, and in the null space its value, its image is equal to 0. Now just understand the basic idea of a projection. Now we go to the first theorem. So just what is the statement of this theorem? So this is very important theorem. So one question will be asked on the basis of projection in the examination. So there are only 2 and 3 theorems, they are problems related to projection. Now if P is, suppose if P is projection, if P is projection on a Banach space, Banach space B, if P is projection on a Banach space B and if M and N, if M and N are the range, and null space, range and null space, then prove that M and N are closed subspace of B, such that B is equal to direct sum of M and N. So it is the statement of the first theorem of projection, so in which my aim is to prove that B is equal to M plus direct sum of M plus N, and the given part is P is projection on a B. If P is projection on a B, so M and N is a range and null space, then we can write it as B is equal to direct sum of this M and N. So this is the statement, so which is a very important result. Now, solution or proof, right? So in the first step, since P is projection with range M and null space N. So that is given if P is projection on Banach space B with range M and null space N, then it means by definition P is number one linear because it is a transformation, number two idempotent, and number three continuous, linear, idempotent and continuous with M is its range. So this is P of Z such that Z belongs to B, and null space which is N. So this is a all vector Z belongs to B such that P of Z equal to 0. So suppose this is equation number 1. So this is the given definition of a projection. So first, since P is projection, then it satisfies these conditions that I have written in this form. Now my aim is to prove that B is the direct sum of M and N. So to prove that result, I take let Z belongs to B. So my aim to prove it is a direct sum of this. Now consider if Z belongs to B, then P of Z is equal to Z itself. If itself P of Z is equal to this values, so this can be written as Z which is equal to P of Z, which can be written as PZ plus I minus PZ. I minus Pz. So I just write once again. So just this Z. So I consider this Z that can be written as, which is Pz plus Pz plus I minus P of Z. So this Pz cancel to each other. So left hand side is equal to right hand side, where I denote the identity transformation. So suppose this is equation number 1, where I denote identity transformation. Identity transformation. I adopt the identity transformations. Now just see that if I write it this, so one thing is clearly P of Z, because it is an image, so it belongs to range of P. So what is range of P? So this belongs to M. So clearly this PZ part, it belongs to M, because it is a range of P. So PZ belongs to M. Also we know that P of I minus P of Z, so this values. So this can be written as, this is a P minus P square into Z. So P is idempotent operator. So this can be written as P minus P of Z. So this can be written as 0Z, so which is equal to 0. So if the image of this term is equal to 0, so it implies I minus P of Z, which belongs to null space, which is equal to N. So first part belongs to M and second part, so first part belongs to M and the second part belongs to the N. So it means Z, which is a vector of B, which belongs to M plus N. So it implies B can be written as M plus N. So this is M plus N. So B can be written as M plus N. So this is in this way we can write it as in the term of sum. Now after that, this expression should be unique. This expression should be unique. This is a decomposition. So we decompose the Z in term of x plus y. X belongs to M, y belongs to N. So this expression should be unique. So to prove the uniqueness, I take Z is equal to x plus y, where x belongs to M and y belongs to N. If I take in this way, Z is equal to x plus y, x belongs to M and y belongs to N. So to prove the uniqueness, so what is P of Z? So what is P of Z? So this is a P of x plus y. P is operator. So this can be written as Px plus Py. Now this y belongs to N. So its image is equal to 0. If image is equal to 0, x belongs to M. So its image is equal to itself. So this can be written as x plus 0. So what we get? We get P of Z, which is equal to X. This value we get. Now second, I minus P of Z. So what is I minus P of Z? So this can be written as Z minus Pz. So what is the value of Z, which is X plus Y, and what is the value of Pz, which is X. So total sum is equal to Y. So we get the value of this, which is equal to Y, and we get the value of this, which is equal to X. So Z can be written as X plus Y. So what is X? X is Pz, and what is Y? Y is I minus P of Z. So it means this expression is unique. So if this expression is unique, then it means B can be written as, so it means B can be written as M direct sum of N, because its expression is unique. So we can write it as in term of direct sum. And third part is to prove that it is a closed subspace, yani M and N is a closed subspace. Now we know that the continuous linear transformation, the null space of continuous linear transformation is closed, as we know that. So since N is null space of a continuous transformation P, so null space of continuous transformation is closed. So it means N is a closed subspace, number one. Now what about the M? So what about the M? So also M is also closed. Why? So M, what is M? M is a null space of P. M is a range of P. So this can be written as Px such that X belongs to B. So this is a range of B. My aim to prove that it is a closed. Now in this case, the definition of a range, its image is equal to itself. So this can be written as, since Px equal to X, since image of Px equal to X, so this can be written as all X such that X belongs to P of X. So this is a M. Now this can be written as X such that this can be written as I minus P of X equal to 0. So what we get, it is again a null space, but it is a null space of I minus P. So this is a null space of I minus P, and it is again closed. So if it is again closed, then M and N are closed subspace of a Banach space B. So M and N are closed subspace of Banach space B. So that prove our theorem. So in this way we can prove that if P is projection, then it defines, it proves the given condition. Now second theorem is, again it is very important. So what is the statement of the Second theorem. So let B be a Banach space. Let B be a Banach space. So that is first given part. And M and N. M and N, these are closed subspace of B. So M and N are closed subspace of B such that, now this is a given part, such that B is equal to M direct sum of N. B is equal to M direct sum of N. So if Z equal to X plus Y, if Z equal to X plus Y of, if Z equal to X plus Y is the unique representation of a vector Z, is the unique representation of a vector Z belongs to B. So it is a unique representation of the vector Z in B as sum of M and N. So where X belongs to M and Y belongs to N, or we can say that as a sum of vector in M and N. Then the mapping, now we define a mapping. So this is a given part. So then the mapping, so this mapping is P defined by P of Z, which is equal to X, and its image is equal to X, is a projection on B with range M and null space N. So this is a converse of the previous theorem. It acts as the converse of the previous theorem. So my aim to define the mapping, which is a projection of the on a Banach space B with the range M and null space N. So to prove this result, so just go through step by step. So first I define a projection P, a mapping P from B to B, and this is defined by P of Z, which is equal to X. P of Z, which is equal to X, for Z is equal to X plus Y as given. X belongs to M, Y belongs to N. So I define this mapping. Now clearly from this, since x which is equal to P of z, so clearly it belongs to range of P. So x vector is clearly belongs to range of P. So it implies M is range of P. Range of P. Why? Because x vector belongs to M. So every vector of M belongs to range of P. So it means M is a range of P. Also P of y is equal to 0. Also P of y is equal to 0. Why P of y is 0? Since z equal to x plus y, so Pz is equal to again Px plus Py, and Pz is equal to itself z, so this value is z, and this value is equal to x plus y, so this is x plus y, so this Pz is equal to x, so it means this x is cancelled to this y equal to 0. So also we know that P of y which is equal to 0, it means it belongs to the null space. It implies y belongs to null space of P. So if y belongs to null space of P, so it means N is null space of P. So one thing is clear. So M is a range and N is null space. Now further prove that P is idempotent, then continues linear transformation. So to prove P is idempotent, next step, P square z, to prove it projection, my aim to prove it is as a idempotent. So this is a P of z. So what is P of z? So which is a P of x. Why? Because P of z equal to x. So remember this. If it is a P of x, so P of x is again equal to x, which is equal to P of z. So what we get? We get P square is equal to P. Right? So very easy to prove that it is a idempotent. So if P square equal to P, so it means this P which is a idempotent. So no need to prove. After that, it is a continuous. To prove it is a continuous. Now let I take this z. Let z is equal to x plus y, suppose, and x belongs to M and y belongs to N, be a unique representation of z which belongs to B. So this is a unique representation of z of B. Now I define some new norm. So one norm is of B. So I define a new norm, define a new norm on B. So one norm on B is already exists, that is simple norm, and this is we define it second norm B. So this is a norm of Z dash. So dash, जो dash है, it is a new norm, and the old norm is this x plus this y. So this is a new norm of a vector Z that can be written in this way. Now since B is Banach space, so we define a new norm. So B is a Banach space. So this norm, we know that this P of Z, norm of P of Z, this can be written as P of x plus y, which is x plus y, so which is norm of x. Why? Because its value is px plus py, at py 0, at px it is x, so this is a norm of x. So this can be written as norm of x plus some positive term, that is a norm of y. So then it will become norm Z, a new norm dash. So what we get? We get norm of Pz is less than equal to norm of Z dash. This is a new norm. So hence P is a bounded operator. So P is a bounded, or we can say that it is a continuous, because in the Banach space every bounded operator are continuous and every continuous operator are bounded. Now this is a sum. If we take B as B dash with the norm dash, and it is a simple B with the norm. So if I take B with the simple norm, so I write it as B. If I take B with the new norm, then I write it as B dash. So remember that all the element of B are and B dash are same, but the difference is when we operate with B, then we apply this norm. When we operate with B dash, we apply this norm. So remember this thing. Now I define a map T which is from B dash to B. So I define, let B dash to B be onto identity mapping. Be onto identity mapping. Identity mapping. It means that T of Z is equal to Z. Why? Because elements are same. So only difference is when we operate on this vector, the norm is dash. When we operate on this vector, in that case norm is a simple norm. So from this, just see that. So this is a B dash. This is a B dash. First understand. And this is a B. Clear? Now this is a T operator from B to B dash. This mapping. And this is a operator Z, and this is a T of Z. So T of Z is a member of B. So it means we will operate a simple norm, and Z is a member of B dash. So we will operate a norm with the dash. So that what we get, norm of Tz, which is equal to, so norm of Tz by definition it is equal to norm of Z. So this is norm of Z. So what is this? It is a norm of x plus y, these values, by using triangle inequality in this norm. So this is equal to norm of x plus norm of y. Now it convert into new norm. So what is that? That is norm of z dash. So it convert into new norm. It shows that T is 1-to-1 continuous linear transformation. It shows that T is 1-1 onto continuous linear transformation from B dash to B dash onto B dash to B. So if I write onto here, then there is no need to write it. If I did not write here, then it is B dash onto B. So at one place we will write the onto. So it means by open mapping theorems, T is homeomorphic and B dash are homeomorphic. So hence P is B to B dash is continuous. So its converse part. So by open mapping theorem, So what is the definition of continuous? Continuous 1-1 and onto. So this is a continuous open mapping and 1-1 onto. So T, B and B dash is homeomorphic. If it is homeomorphic, then from B to B dash, it is homeomorphic. B to B dash is continuous. It is continuous. So what we prove? We prove that P is idempotent. P is idempotent, number one. Number two, continuous. So if it satisfies all the property of projection, then it means P is the projection on B. So it means P is projection on B. Projection on B. So which prove the result of projection on Banach space. So these are two theorems. So these are very important theorems, and one theorem may be asked for examination.